Hello, all and sundry. If you can hear me.
Yes.
Hi. Hi there, Seb. How are you getting on?
I'm going well, thanks, Alf.
Buoyant flakes everywhere now?
Sorry, what?
Buoyant flakes floating around the oceans everywhere now?
Not quite yet. Unfortunately, much more like buoyant dead birds floating around our shores.
Oh, we don't want that. We don't want that.
No.
That's very sad.
Very sad. Hi,
Buoyant dead
Jesper.
birds. Mm. Well, good morning, evening, afternoon, everyone. Uh, uh,
Hello.
Hi, Alf and Jesper,
Hi.
uh, our youngest diehard attendee. Um, and I won't say, won't follow that with anything about you, Seth.
Right.
Um, everyone's welcome. Right. I've I hope you don't mind. I've kind of made a decision to do a presentation myself today, and actually we have Dale Ann is with us, as one of the people that we've been talking with. So welcome, Dale Ann. Right, and so let's get to it. We'll do our usual format, which is to set the agenda. I don't want to completely monopolize the meeting this evening.
Why not?
Why not? Well, maybe I should. I've got a presentation here. I've done what people like me always do here, have too many slides, but I'm going to whiz through the early slides and so get to the kind of nub of it, which is all about using sulfur aerosol for marine cloud brightening. And this is not to say
What happened to your other forms of aerosol?
what do you mean, like iron 3 chloride?
No, you were having some other gaseous ones, I think. I thought
Yeah, yes. Um, this is a sulfate aerosol.
based on ammonia.
Yeah, so ammonium sulfate, it's still a sulfate aerosol, ammonium sulfate.
Oh, okay, right.
So it's there's we're not this is not a kind of if Franz is here this evening, hopefully Franz will be here. He's really the original originator of this. He said, why don't you do it by mixing gases? Um, you know, so I'll get to that. I'll get to that. We haven't all agreed on exactly how to, the best way. And in fact, I haven't even settled it in my own head. There are different options. And so I'll get to that. So anything else that I want this to be the main thing? It's been a while since I've put something across. Mainly we have other people's things, other people's
So, so I,
topics. Yep.
yeah, I have something
Glenn?
that, I put together several $billion worth of proposals for SAI and marine cloud brightening. And these files are open source. They're on the internet. So I could give the 10-minute tour of these files and
Okay.
not get into details, but just say that if you're interested in getting an idea of what does it take to, let's say, solve the entire problem with R&D, with a massive R&D, what does that look like? And without getting into detail. So that's like 10 minutes.
Okay. Right. Okay. 10 minutes. Okay. Let's make time for that. And Greg in USA.
Thank you.
Greg?
Well, yeah. Again, this is something that it sounds like there's going to be a full schedule anyway, but interests me is that the interpretation of decreased albedo decrease. The discussion that was had. Now I'm geezing whether it was the NOAC or that HPAC, the last HPAC.
Yeah.
Where two people presented. I guess that was HPAC. Jan and perhaps two people, but they were talking about
Tom, Tom, and Jan.
Yes, I thought it was Jan, but
Tom Harrison. Yeah. Jan.
yeah. Right, that was it, exactly. Anyway, to quickly say it, I mean, they were talking about these recent heat waves, the proliferation, and the association with El-Ninos and super El-Ninos and like that. And I read something in between by a post by everybody's favorite scientist, whatever his name is.
Jim Hansen.
Hansen, right, all our hero,
Yeah.
or whatever. And he said they're right about the aerosols, not specifically talking to these guys, but they're right about the aerosols. They've got the methodology wrong. And I must admit that
Wasn't he saying that the El Nino is not such? It's not so much the El Nino; it's the underlying
exactly. You said
accelerating
everybody's
warming.
focused on El Nino, but that's if anybody has any comments on that, who has anything to add to that, I mean, it's a question for those two, Jan and Tom, or
Right.
John and Tom. But that's my question, and it can be ignored if no one really has anything to say about it, which is quite possible. But it was interesting to me. That's all I have.
Great. Okay. Thanks, Greg. As you know, I do welcome these suggestions, and I still do. Thank you. Okay. All right. So I'm going to go with all this.
You got two more.
Oh. Okay. Go for it. Sev, please.
Just I dipped into AI, and I was just finding out how good was Singapore at being a good country for doing cooling experiments.
Mm-hmm.
And in 1 second, it came up with what seems a very, very good idea. So I'm wondering whether some of the other HPAC members might care to do the same things for different countries, so we can later on compare them and see which countries are best for Glenn's work and for other ideas.
Okay. Joint effort. So you invite people, basically. You're inviting people to identify countries for cooling experiments, is that?
Yeah. Using AI.
So, yeah.
Basically, we all research countries and find out what AI, AI reports on their whether they're favorable toward any given country to actual experiments in what ways.
Yeah.
I'd be interested to know what Sev Clark found about Singapore. They sounds very excited about, but that's for a different occasion again.
I've sent an email on that to Robbie Tulip. I can. It's a bit long, so if you send me an email and say you'd like to see it, I'll send it to you.
Okay, cool. Thank you.
Okay. Right, got that.
Me on that list. Brian, I'm going to Singapore next month, and I'm going to be participating in the Impact Week for that. In addition, for several years, we've been participating in the Singapore Livability Challenge, which has a cooling prize. We simply need them to expand their horizons a little bit to think about cooling deeply rather than little tactical moves. So would be very interested in that. And greetings from New Delhi, India, where we had a fantastic reception last night for the India Cooling Summit. Mm-hmm. And in 8 short hours, we'll be getting the India Cooling Summit. I've met last night with Professor Allen and several others on our panel. And it's going to be an exciting day. We've met ministers and great dignitaries that are preparing, and it's going to be an exciting summit. And I hope I can report the results to you in 2 weeks' time. So we're on the eve. It's late at night, but I've got a bit of jet lag, so happy to be listening tonight.
Okay, thanks for joining us, Brian.
Brian, could I quickly ask, do you know if any of that will be made available via recording or even live coverage?
Well, I think there'll be some informal recordings made of the various sessions. I hope they do, because the stratospheric aerosol session will be in parallel this afternoon with our marine cloud rebrightening session. so I will miss the SAI, but hope that it will be recorded. So I'm checking with people on those details and hope we can share the results shortly.
Yep.
Perfect.
I was told they're
per-
recording the geoengineering conference in India.
Okay, that's it then. Yes, perfect. MCB and SAI are set up to be enemies by putting them opposing each other. Brilliant.
Well, they're parallel sessions. This is all about it's really waking up the entire forces
I know.
here.
I
And
understand.
we have a great opportunity and engagement with government officials across India and beyond. I spoke with representatives from Bangladesh, from Assam, and across Southeast Asia. I'm very enthusiastic based on our reception last night and looking forward to the energy going into the summit. And I'll be spending the entire month of August touring India and having further discussions with political leaders, commercial stakeholders, and civil society participants. So
Sounds
we're
great.
leaning
Great.
into India leading the way towards climate repair for the global south starting tomorrow.
Fantastic, Brian. Okay, and so it's kind of what, 3 o'clock in the morning for you now, or something like that, or maybe even later, 4 o'clock.
It's 1:30, so I think I've just done my presentation, but I'm looking forward to hearing everyone's
Exactly, that's what I'm thinking. So
speeches as I drift off to sleep again.
yeah, that's kind of why I'm letting you kind of do your presentation now, because you might not be with us later on, given the time. Okay, thank you, Brian. Ron Baiman, please.
Yeah, just a quick comment. Iceland that's declared a climate emergency, and what to do about getting the IMO to do something about their termination shock. I just had to post about that to a bunch of people, including Robbie and others. So, but anyway, it's always curious to me that this is such a very practical, relatively easy thing to do that would act much more quickly than the various other things that we need to develop, scale up, etc. So that's it.
What is stratospheric aerosol injection, or just SRM in general?
No. I'm talking about a
Temporary something? We've lost you, Brian. Ron.
full thing
I think
to
he's talking
reverse.
about
Yeah,
a temporary
you
regeneration
get
of
it?
aerosols from tip tracks.
So say again, please, Brian, because I lost you at the crucial moment. Ron. Brian, what was it again?
If Ron's not available, I think he's referring to a temporary regeneration of aerosols from ship tracks.
Okay.
That could be done
Right.
either with
Yeah.
reversal of
IMO
the
regs.
IMO decision
Right. Yeah.
Which is the
or
subject of
longer
Clive's talk.
term submicron sea spray.
Right. Yeah. Okay. Right. Thank you. Great. Okay. That's going to be plenty for today. Thanks, everyone. So now, let me jump into my presentation here then. So, and this is going to leave a good half an hour for everybody else, and we've had 15 minutes. So I've got basically about 45 minutes, and I think that's actually plenty for my presentation. Okay, so this is what I've been working on. And this isn't really that much new necessarily to people here. This is the kind of thing we've been talking about for a long time in this meeting, but this is going to be put up as a public video on YouTube. And so I thought it was a good opportunity to put this across. Okay, what I, and particularly a gentleman called Paul Stansel, who's a PhD physicist, he tends not to like these meetings. He thinks we're a bunch of windbags. And if without numbers, none of it really matters. And so he's been extremely good. He insists on, you've got to have secure numbers. See, he's not here actually. So he and I have anyway been working on this together, but it was originally inspired by Franz Oster, who I think also is usually here, but he's not here tonight either. Okay, so can the cooling from air pollution be safely mimicked to cool the oceans? Let's see what you have to say about this. So I'm going to whiz through, and mainly I'd like to have questions at the end, unless you think there's something glaring that I've missed or whatever. Okay, I think it's very important to interrupt. as we know, the oceans delayed climate warming. Yeah. And the reason is because the oceans have high, well, big reason behind this. This is a big, broad brush rather than scientific, detailed scientific. This is so you can get an overall understanding. The oceans have very high heat capacity. It's been taking a lot. It takes a lot of heat to warm them up. The water has a high heat capacity. The cold oceans delayed the self-reinforced feedback warming and these are the main feedbacks that have now got going. Increased water vapor. So you've got warmer oceans, you get more water vapor in the air. That traps heat, just like greenhouse gases. Okay. And as we know, we've been discussing this pretty much every fortnight. The cloud loss at low latitudes, so the tropical and subtropical latitudes, we're actually losing clouds, cloud reflectivity, and this is where the sun is strongest. So there's a form of sort of global dimming. It's kind of contradicted by a graph I've got in a moment, but we can discuss that. There's a lot of talking about global dimming in parts of the ocean, right? And of course, sea ice. So I think everyone understands that if you lose the reflectivity of sea ice. So we've got lots of reflectivity, and we've got increased heat trapping with water vapor. These are the feedbacks. This is why the effects amplify. Warming during the 2000s was already rapid on a geological timescale. So this is partly here for anyone who still thinks climate change is really not a problem and should basically be ignored because of whatever reason. We're probably not going to move. Obviously, we're not going to move the needle on those people. But just here's what we know. The best we know. The worst mass extinction, Permian extinction, 250 million years ago, 90% of species died. This is just an artist's impression. It warmed 10 degrees centigrade. This is what Jim Hanson's been saying that we'll get here with climate change after maybe some number of 100 years. Nobody knows if it'd be 400 years or what, something like that, maybe 1,000 years. It's going to be, with nothing done, 10 degrees centigrade rise. The Permian took between 10 and 100,000 years. So that's this much per decade, 0.001 and 0.01 degrees per decade. And that now we've got 0.1 degrees per second, at least. This is during the 2000s. So that's 10 times, 10x, 100x faster. Could life adapt? It didn't adapt very well 250 million years ago. Is it going to adapt in a few hundred years to a 10 degrees centigrade increase? I mean, I think the short answer is no. And since the 2000s, warming rate has more than doubled. So it's even worse. And this is all bad news. It's not news to those of you here. You've heard all this before. This is, I've revised these figures down to make them conservative. This is not the Jim Hansen number. He puts in 0.36 degrees per decade. But if you do a AI search, it won't say that. It'll just say 0.27 because this is more people would agree with that. But anyway, it's still more than doubled. Of course, the warming rate is driven by Earth's energy imbalance, and partly the reason putting this really quickly, this was when I changed my mind, when I changed my mind from I don't know, but I don't understand this climate change stuff to okay, it makes sense. Yes, okay, there's a reason for climate change. The reason is, and I've used a term here, once again, my friend and colleague Paul didn't like this term. He said, that's not a scientific term. What's that doing in there? Arbitrage. This is a term that's used by finance people who say that, this is like the difference between a buy and a sell price. I'm trying to use an analogy here that's a bit more understandable to kind of hard-nosed finance people. I hope some of them will watch this because they understand, you buy at a low price, you sell at a high price, you make money basically. So they understand that. And hopefully big numbers, so and the amount, the difference can be quite small, but you still make plenty of money if you're making lots of trades. Okay, what goes on with the Earth is every day an enormous amount of energy comes in, and this is broken down by scientists to every meter squared. So on average, it's a 240 watt light bulb every square meter of the Earth on average, right? That's the amount of energy that comes in. That would fry the Earth very quickly if it didn't warm up and then retransmit that energy back out again to space. And the energy comes in as what's called shortwave, basically visible light and UV. That's how the energy gets down to the surface. And it does not heat up the Earth so that it's white hot. It doesn't get that hot, otherwise we would be burnt to a crisp. But there's enough infrared energy. So it's just infrared energy that how the Earth loses its energy out to space. And since the Earth's been warming up a little bit, it manages to lose that same amount of, it's still a 240 watt light bulb that's of loss, but slightly different. Okay, so the amount of energy coming in is 240 point whatever 6. The amount going out was 240 point, I don't know, 3 or something. Difference basically shows you this is the energy imbalance. It's the difference between. This is like the arbitrage between two prices. This is the amount of energy difference. We've got a little bit more coming in than going out, and that was what was driving climate change. That difference in energy flow in 2004. But the thing is, we've got more energy getting basically trapped or not getting reflected by clouds, you could say. And okay, the Earth has warmed up, so it's retransmitting a bit more energy. This is kind of a negative feedback, if you like. It's where it feeds back by emitting more energy out to space, but it's not enough to catch up with the extra amount getting trapped and not getting reflected. So we've got a bigger energy imbalance. That is what's driving a faster warming rate for the Earth. Okay, so enough of that. That's a very, very rapid explanation for those without much time. Okay, we're now going to talk about marine cloud brightening. This has been proposed by meteorologists for decades. Sean Twomey, I don't know, 30 years ago, he's long gone, I'm afraid. And he did a whole lot of measurements and proposals and math behind, if you can brighten clouds, brighter clouds reflect away more sunshine. That's the bottom line of this slide here. And it was done, it's still happening accidentally, from pollution, from not only shipping, but, coal-fired power stations. A lot of it's getting cleaned up, so the clouds are not getting brightened as much as they did. So the way this works is that clouds are essentially just dew that's condensing onto aerosol particles that are up there. There's always aerosol particles in the air. Not so many over the ocean as there's on land. And so, which means marine clouds can be rather easier to brighten. Not everywhere, it's not always the same, but in essence, that's what can be done, and that's what has been happening. There's a certain amount of water in a cloud. If it's spread over more droplets, then mathematically you end up with a bigger surface area. Same amount of water, but larger surface area because it's spread over more droplets, and so therefore it reflects more away. And there have been many, many, many papers from meteorologists and scientists on marine cloud brightening and how much cooling it could do and the effects, and a bit more on those actual amounts later on. Yep. So here is the warming influence, the effective radiative forcing. So the point of this, again, people have seen this many times. The point of this is to point out to those who haven't noticed yet, like the United Nations environment. I'm very bad. I shouldn't point the finger too much at people, but they don't seem to have noticed that the IPCC has been talking about the anthropogenic cooling influence for a very long time, as well as the anthropogenic warming influence. So this is greenhouse gases, and everything gets separated out. I mean, scientists have done an amazing job of giving us this data, and they can separate the components. Say, look, there's the warming component. That's how that's been increasing. And here's a cooling component, and how that's been kind of increasing, but it's going, as pollution gets cleaned up, it's getting less. And you can add these two together. If you add them together, you get this is the overall picture. And numbers matter, 3.1 watts per meter squared. Doesn't sound like much, but that's enough to cause a warming effect. And it's much more now than it was, in 2000, which is a lot more than it was in 1950, much smaller. So climate change wasn't really noticeable then. It's much more noticeable now because it's being driven by this radiative forcing. Now, but as I said, bottom line, there's cooling has been taking place, and it doesn't usually get discussed by the media, but it's very important to know that it has been going on. And so people say, oh, no, you can't do any cooling because there might be risks. Well, it's been going on already. Too late, mate. It's already been happening by accident. And so then Jim Hansen, in his various papers, so the importance of this slide is that, we think we're in a fix because the temperature is warming up. And we've been told, you've only got a certain carbon budget, and if you burn all that, then you're committed to 1.5 degrees centigrade. And Jim Hansen is saying, well, you've been underestimating the amount of cooling going on. So not only has there been cooling going on, you've been underestimating. It's actually been more cooling. So in a way, it's been good, but which means it's skewed your calculations on this very important thing, climate sensitivity, which is how sensitive. Climate scientists for decades have been saying, well, look, we need to know how sensitive the climate is to adding greenhouse gases to the atmosphere. And for a long time, that it wasn't really questioned. Well, not in the mainstream. 3 degrees, yeah, we've worked out that it's 3 degrees, and from that we can tell you how much carbon budget you've got, how much more coal you can burn before we go past 1.5. And Hansen's saying, no, the climate is likely a lot more sensitive than 3 degrees. So if you double your carbon dioxide in the atmosphere, you're going to get more like 4.8 degrees, and here there was give a certain uncertainty here because you didn't count the amount of, you thought it wasn't too bad because you were not counting the cooling, which was actually more than you thought. So without getting all into that, there's a bigger danger here. So, I read that apparently this is child mental abuse, that all this worrying and climate alarmism is child mental abuse. But we don't really see it as that. We just look at numbers and we extrapolate lines, and we see that it's not going to get any better anytime soon. It's just going to keep getting worse unless some direct cooling is done. And that's what this is all about. So moving on to sulfate aerosol for cooling. This is what this presentation is really mainly about. And sulfate aerosol is not harmful in low concentration because, when we start talking about sulfate, putting aerosol in the air, naturally, anybody, and especially people like me as well, would say, hang on a minute, hang on. Don't put aerosols in the air. You're going to just poison us. Well, again, too late. It's been going on at sea from shipping for a very long time. And actually, the International Maritime Organization have got new rules. But mainly, it's because ships sail close to coastlines, they go into ports, and this is the main problem. Sulfur dioxide does cause respiratory illnesses and shortens people's lives, and so they've cut that off. But sulfate and sulfur is in our bodies. We wouldn't, survive without it. It's been in the ocean since the beginning. The smell of the sea is mainly the main component of the smell of the sea, which we all love, is dimethyl sulfide, which is not a very nice substance. But in small quantities, these things generally don't matter. They're not toxic in small quantities. And in the air, dimethyl sulfide basically forms cloud condensation nuclei. So this is the aerosol particles on which water condenses as dew to make cloud droplets. So the more CCN near a cloud, generally the brighter it gets, because we get more cloud droplets, okay? And so it's formed naturally, especially in estuaries and wetlands. We get the smell of the coast. So why did the International Maritime Organization impose a blanket ban on high sulfur fuel emissions even far out at sea? And this is what we've been railing against, and Ron has organized us to produce a paper, which he's trying to promote, with basically a letter to the IMO saying, can you reconsider your decision to ban sulfur emissions far out to sea where it doesn't really do any harm? And they haven't really replied to us. But I looked, again, AI is a wonderful tool, and it said to me showed me various documents and said, well, it's a lot easier to verify compliance with the rules if they just make it a blanket ban. If they say, well, you can do it here, but you can do something else there and something else in different places, people will game the system. And so, that's what they've said. It's a blanket ban wherever you are. You can only burn low sulfur fuel from your ships. However, the kind of slightly promising aspect of this is not really news. The London Convention, London Protocol Secretariat, which is administered by the IMOs, it's kind of an arm, or you say part of the IMO, recognize marine cloud brightening as, and this is what they say, a principal marine geometry, requiring evaluation. So this at bottom line is, we think, given the dire situation, we know that shipping had a cooling effect. Maybe this could work. We can request and say, would you consider this? Would you consider special purpose marine cloud brightening vessels licensed so that, so that they could at least do research on marine cloud brightening far out to sea? Okay. Now, I know it's not as simple as that. I'm giving you this broad brush picture. Okay, moving on. Why commercial shipping cannot cool the oceans? The reason is because shipping lanes, which have had a cooling effect, again, uncertain exactly how much, different scientists say different things, but they all pretty much say it's had a cooling effect. It's just a question of how much. But the thing is, shipping lanes, they only affect about 10% of global ocean area. The cooling effect only strongly affected about 10% of the global ocean. So here's my analogy. It's on right. You're on a hot day.
Yeah.
Yeah.
Hi, Odie.
Can you mute?
I'm listening to video,
yourself,
but I heard the Odie voice.
Can you just mute? There you go. That's right. It's like putting your arm in the shade on a hot sunny day. It does help a bit. It'll help you cool down if you put your arm in the shade. But it's not the same as actually putting you put your whole body and just go and walk into a place that's a nice shady spot. So that what we need is lots of area to be brightened. It's not really practical to brighten all these areas very much. It's only really a few percent, but over a wide area, it's enough to provide enough of a cooling effect that's can actually halt the warming. So we've got some numbers coming up in a moment. Yeah, so widely dispersed MCB has a much stronger cooling effect, and especially in what's called the most susceptible areas from marine cloud brightening, where clouds brighten most easily. Tends to be the west coast of the Americas like this. I think we've seen some of these maps before, but yeah, seem to be about 10 from mod areas from strongly susceptible to moderately susceptible. So quite a large area of the ocean in the end can be brightened, including, I think, somewhere in the Indian Ocean. Right. So up to now, it's been sea salt aerosol particles. If you read any paper on MCB or look up marine cloud brightening, these are meteorologists. They mostly think about clouds and they think about aerosol particles, and they do all their calculations, and you can find out how much cooling's going on. So most of this work was done by Paul Stansel, my colleague I've been talking about, who talks to me about these numbers. He said, look, it's 10 to the 17 particles per second per ship. That's an enormous number of particles per second. That's 100 quadrillion particles per second that all have to be the right size. Some of you will remember Stephen Salter, very much an MCB pioneer, really introduced it to us here. Talked about monodisperse, the same sized aerosol particles. Well, you try making 100 quadrillion aerosol particles, they're all, nanoparticles. They've all got to be the same size. That's a big ask. But effervescent nozzles, this is what Cambridge University have been working on, amongst others, can get close enough, and they've been able to make 10 to 15 particles, 100 times less, and with the right kind of aerosol profile, nice size, tight size distribution. But the thing is, when you scale this up to go to make it 10 to the 17, the amount of energy is enormous. You need, it's the power of a big ship. And so we talk about feedstock as, sulfur and other substances. You've got to have hoppers of this stuff. It's still not much compared to the huge wide area, because these are tiny, tiny nanoparticles. We're not talking about huge tonnages of the stuff. It's replacing what used to be naturally in fuel in ships, in shipping fuel. So that sort of 3% that was in the fuel, that's what we're talking about. But just to do it with sea salt, because you've got to generate so much power, your feedstock becomes bunker fuel. You've got to burn all that fuel, unless you've got, I don't know, a nuclear powered ship. And so that is a bit of a downside and very expensive, just to buy the fuel. And that's even before you think about the CO2 emissions. So really, puts a bit of a question mark over MCB, all that great work they've done, if the energy requirement is too much. But as I said, yeah. So anyway, before I move on, what's the cost? And so again, Paul says, don't just talk about it, work out how many. And so he worked out with a huge code base, 2,500 ships. Actually reduced it down a little bit, and we'll see it, unpack it in a moment. 2250 ships operating pretty much continuously, burning all that bunker fuel to pump all that water to make all those salt particles from effervescent sprayers, 90 billion. I worked out this here from with your ChatGPT told me if you do that, and I gave it the numbers, said, all right, 1 million tons. Still a good investment. If you want to avoid climate catastrophe, Paul produced this again. We've sent this out to a few people recently. So he worked out from a paper on economic costs from this gentleman here, Guillemette, and worked out. So here's below the line is your cost. So you've got an annual cost of 90 billion. And the benefit and avoided costs is the blue here. And every year that you just halt the warming, instead of just allowing it to get worse and worse and worse and worse and worse, we've halt the warming. So it just stops getting worse. And so here's the counterfactual. You're saving money, you're saving more and more and more every year compared to what you would have been spending as disaster got worse and worse and worse. And so the difference between the two is the yellow, and net benefit after the first year of halting warming. So this, if someone can pay for this intervention to halt the warming, then everybody benefits from the avoided costs. So, right. So, what are there other ways? What's all this about? Other ways to produce CCN aerosol particles? Yeah. So this, as I inspired by Franz Oster, for a long time he's been saying, instead of pumping to make droplets, just do it the way nature does, which is you have gases that react together. This has been going on millions of years on the above the ocean. The ocean produces very small amounts of, as I said, DMS, dimethyl sulfide. There's a lot of chemistry. It produces sulfur dioxide. You get ammonia from the ocean. Franz points out that the ocean, as it acidifies, it produces less ammonia, small amounts of ammonia, but enough to react and produce aerosol. But these aerosol particles are so tiny, you don't see them. And so, gas phase particle synthesis has been going on for millions of years. And Franz says, just do that. I shouldn't say just. It's quite difficult to do in a reactor. This is what I've been looking at. Can we make 10 to the 17 particles per second in a reactor by reacting, the right chemicals together in a ship? And, it says, well, yeah, but you've got a huge scale-up problem. There are systems. Companies make aerosol production, little, equipment for laboratories, but it's nowhere near 10 to the 17. It's more like kind of 10 to the 8, so you've got a huge scale-up. But nobody's ever tried it before, so it may be possible. It may be possible. So I've done that, and it gave me a design, and it said, here's where you need to have very precise engineering to make sure that everything's done properly, and you don't get sort of too much concentration, producing too many large particles. I could go on and on about that, but not now. So then I thought, well, how did shipping actually work then? If it's so difficult to do, accidentally shipping was doing this cooling, how did that work? And it told me that you've got to have seed particles that grow in the marine boundary layer, so basically in the air above the ocean. And the soot and unburned hydrocarbons, basically muck that comes out from the engine, including sulfuric acid vapor as well. So this sulfuric acid vapor condenses onto these particles. Sulfuric acid is very strongly water loving. It's hygroscopic, it attracts water, so it makes excellent cloud condensation nuclei. And we know, so this is obviously, we know that shipping has done this, had its cooling effect, and here it was telling me, and it's kind of a multitude of different things. The cooling happened and the marine cloud brightening happens actually in different ways at different times, and especially, it also depends on the weather condition. But it's known, it's knowable. You can find out how it's been going, what the chemistry is, and what conditions, and by how much it brightens clouds at different places. So this makes me think, well, why not mimic that process that ships have been doing accidentally, but not by burning huge amounts of bunker fuel, but instead by seeing how closely you can mimic, seed particles. And basically the system is saying, we'll just make them from ammonium sulfate, make small seed particles, let them grow in the marine boundary layer. Okay, so I'll leave it at that, because it's pretty, once you start talking about chemistry, it sounds horrendous. But the thing is, okay, but there are big benefits. Once you kind of accept, you can talk about chemistry. It cuts the costs by, these are broad brush numbers. Obviously, you've got to look into them more, but I think that's credible. If you don't have to burn a huge amount of bunker fuel, you just actually sulfur burns. It can burn in air, and it's cheap. You don't want to do it, don't do this at home. Okay, but reduce the cost and reduce CO2 emissions enormously if you're not burning bunker fuel. You're just burning sulfur in a controlled, proper way that's properly researched. Okay, and other feedstock substances as well. Right. And that gives you opportunities. We can do optimization. So rather than just send the exhaust out of a big ship's engine, which has been doing a good job on its own, we understand how that process works, and we can optimize it. We can set the particle size to be the best size for so clouds become supersaturated. The air goes up. As we know, air gets colder as you go up. It gets so cold in the end, can't hold its water. You get dew forming on particles. That's called the dew point. And the air becomes supersaturated. It means it just can't hold it. It's so saturated with water vapor, it just can't hold it anymore. So it comes out as dew. Anyway, so this is what marine cloud brightening papers talk about all the time, supersaturation level. So it's part of the science of it. This is our main research proposal. Okay, that's mine. Okay, I think I should come out and say it's my own proposal. We're still discussing it, Paul and Franz, and we're trying to get other people in the conversation as well. So here's a question: wouldn't that sulfate aerosol acidify the ocean? And once again, I asked it. These numbers will have to be checked, but it said no, not even close. Not even in the quantities needed to restore ocean temperature. You've got to do more marine cloud brightening for that. pH would change over 20 years if you do enough marine cloud brightening to restore the ocean by this many pH units. So the ocean is a little bit over pH 8, so it's actually slightly alkaline naturally, and that is essentially negligible change. But for business units CO2 emissions, we know the ocean is acidifying, but that's overwhelmingly because of the huge amount of CO2 going to the ocean. So you see, we're talking about enough sulfur to provide cooling, but these aerosol particles, when they're nanometer size, even though you have quadrillions of them, it still doesn't add up to much. It's only a sort of kilogram an hour or something like that. It's really not very much. It's amazing how small these aerosol particles have to be, which means it's a small amount. Okay, so the amount of acidification, as you see, 0.3%. Not really enough to worry about. What's more damaging? So here's another question. What's worse? Is it ocean acidification or the actual warming for ecosystems? Of course, the answer was varied. So, well, it depends what ecosystems you're talking about, but it's very good I find Paul's persuaded me to part with money every month on ChatGPT so you can get the top model. And it does a good job of saying, well, let's have a look here and look at, give you a broad brush answer. And it gives you, 10 or 20 pages to wade through. But basically, it said, bottom line, really, the warming is more damaging, actually, than acidification. Acidification is definitely not a good idea. And it is affecting certain things, as we know, shellfish. Anyway, so let's move on to Paul's answers, his modeled answers here. From his code base, how much cooling is possible, model results of using sea salt particles versus ammonium sulfate, really to see the difference in cost. And so he did modeling using what's called a heuristic model. So it's basically simple-ish equations, quite a lot of equations from Professor Rob Wood's paper, which is actually called, here's a heuristic model. He's basically saying, if you want to do some of your own calculations, use these equations because you won't need a supercomputer to run a huge model. You can actually do it with fairly simple equations on your PC. And Paul did that, worked out. So what would be the change in global average forcing? So remember I showed you that picture here of, how am I doing for time? I'm not, I'm on, I think I'm on the, but just about on schedule. This overall forcing 3.1 watts per meter squared, that's what's being, that's the overall warming influence. When we put in the heat trapping from greenhouse gases and the cooling influence from pollution, from the existing pollution, we've got an overall warming influence. It's called effective radiative forcing, ERF, of 3.1. So Paul has worked out, if you want to reverse the warming, you have to basically counter the current amount of heat being trapped. But to halt the warming, you just need to overcome the current energy imbalance. So there's no warming influence. Doesn't mean it cools, it just means it stops warming. So how could those be achieved? Okay, using sea salt aerosol, taking into account you got burn a lot of bunker fuel, billions of dollars. Paul's a scientist, so he uses giga dollars. Okay, so we can see how many billions it costs here for that. I mean, these are much smaller than the costs, which are approaching trillions now, aren't they, for these extreme weather events? I know it's hard to the attribution. There's always controversy. Okay, and percent of the ocean affected. Got to cover 22% of the ocean. These are big areas. Their oceans are huge, so you need a lot of ships basically, or unmanned vessels. But there's the cost, you see, which add it all up. And people say, well, how much brightening does that involve? This is really quite interesting because in this case, Paul has said that the average amount of brightening for a small intervention to only stop the warming, just halt the warming, because you can take the best. Where is it? You only need 22% of the ocean, because you can use those really great susceptible areas where the clouds brighten easily to the west of the Americas and west of Southern Africa. You only need to use 22% of the ocean because they'll brighten a lot, and you'll get still not quite noticeable, but certainly measurable by satellite, a 2% increase in albedo of the cloud. So they're 3%, nearly 3% brighter. You don't really see it with your eye, but certainly a satellite sees it, and it has enough of an effect. That's the overall global, because weather patterns, winds, they spread the warming, they spread the goodness all over the earth. Okay, and so to reverse the warming, you have to use a much larger area of the ocean to brighten clouds that are not so susceptible. And okay, so you get the idea. I mean, partly the purpose of that slide is to say Paul does his homework. He's very rigorous. Okay, so pushbacks. We're all familiar with these. We've discussed them ad nauseum. Termination shock. But what if they stop doing it? Earth would suddenly start warming up much faster. Well, that's already happening today because of pollution cleanup. So the very thing you're afraid of is already happening under your nose. What about the risk of action? So, risk of action versus no action. People say, no, don't do it. But we say, well, what's the risk of taking no action then? And so it's the same kind of answer, really. It's already been happening. The risk is well known. The risk of action. So, yes, okay, to be fair, there could be changes in rainfall patterns. It could be uneven cooling. Some places, some papers even said, no, this place has got a risk of actually getting a little bit warmer. Everywhere else cools down, but this sort of little pocket of land over there might get a little bit warmer. Oh no, we can't have that because they might claim against us. But when we find, the amount of forest fires happening now, this is what we always predicted. As I said, you extrapolate a line and it's going to get worse. And at some point, people are going to start jumping up and down saying, we can't have this. Well, look at the risk of action against no action. The main risk, obviously, was that respiratory disorders. A big funding agency, for example, reinsurance company might look at this and say, well, why should we pay for this? Everyone else benefits and we're stuck with the bill, and plus what's worse, and a very valid concern of theirs and of other climate scientists as well. Well, we fixed the warming problem, so we will go back to our old lives, and people start burning more coal. Because apparently the problem's gone away. And we've had to pay for all this. And it only just gets worse again because people burn more CO2, produce more CO2. It is a problem. There's too many of us and we can't agree, and we all try and game the system. So we have to keep saying this every time. It's not a replacement of greenhouse gas emission reductions. I'm personally a proponent of nuclear power, but let's leave that aside. Right, so this is our call to action. Of course, a coalition is needed. So it's not just left to one group and reinsurers to foot the bill, who clearly they haven't, not going to right now. NATO, we're told, is facing big costs as the Arctic melts. They've got to think about, well, how are we going to keep that secure? Of course, governments, there's a long list here. The coalition is needed of basically responsible groups who can see that if they can get together and agree on a research program, this stuff is available. Scientists have been trying to tell people about these ways of cooling for decades. Alan Gadian, Professor of Meteorology himself, and Stephen Salter, they just said they failed. They explained it to other scientists, and we were all convinced, but they failed to convince, the powers to put enough money into it. So there's been money for research, and there's a lot is known now with papers on marine cloud brightening. Of course, I'm not saying anything about stratospheric aerosol injection because I've only got time to talk about marine cloud brightening here. So this is not saying anything about that. So basically, we need to begin by asking somehow, have someone at a sufficient level to be able to speak to the IMO. We've tried, and it's been very hard to get through to them. But someone at that level to speak to them and say, look, would it be possible? Would you consider? Is it practical to have licensed special purpose vessels producing sulfate in the ocean? If it's far enough from coastlines, would you consider that? So they'll have their discussion behind closed doors and whatever, and then we'll find out. But if it is possible, then there's an awful lot of cooling that can be done without it having to be in the stratosphere. Okay, let's leave all that about the stratosphere aside. If results are successful, of course, fund a scaled up operation. So, okay. So then how much, this is my last slide there, how much to scale? So we're in a happy position of being able to decide whether to, as you saw from my earlier slide, halt the warming. Unfortunately, there's still a risk of tipping points, taking the system out of control. We don't know if that's happening now already or what, or try to restore, make the program big enough to restore ocean temperatures. So reduce the costs of climate disruption. actually reduce them from what they've become on an annual basis now. So it's not trillions of dollars every year for horrible hurricanes, but it goes back to being what it used to be. There's always going to be extreme weather events. So again, we've discussed how long. Some people said, well, governments are going to say, can you do it in 3 years? Well, probably not with MCB alone. And in any case, a lot of people will say that's too quick. It's too much of a shock. You need to cool it down slowly. Just talking about cooling down the oceans is, people just say, well, that's a pipe dream. Anyway, okay. So more time to buy more time for net zero. Net zero is not popular in the UK right now, but it's still vitally important. It's difficult to do. We really are between a rock and a hard place, but it buys more time for that. Okay. All right. So I'm going to leave it there. So where are we now? We've only got half an hour for everybody else's. Any questions or comments? Maybe you have 5 minutes for that. Sev,
Yep.
Please. Yeah.
Yeah, I'd like to do a quick comparison with my ISA aerostat method. Instead of 2,500 ships, you can get away with only 250 wind turbines, and you get using the ferric chloride. You don't have the sulfur problem, so you don't have the worries about people suing you for air problems, and you get the iron fertilization, and these using the ferric chloride, pumping a kilogram per second of ferric chloride up to an aerostat, you get 240 times the amount of CCNs which Rob Wood said was needed. So you're getting hundreds of times better benefit. Why worry about ammonium sulfate when you can use France's ferric chloride?
Okay. Well, I think you'll have to do some modeling, do a paper, justify those claims, Sev. Because if that's right, then they'll be twisting your arm off for information on how that can work. So yes. All right. Thank you very much. Yeah, we'd love to see the modeling on that. And of course, we have the same problem. We say, look, here we are. We've done the modeling, and just to get somebody to scrutinize that costs money. They have to have another scientist who can then do a critique. Greg, please.
Well, thank you for the presentation. I have a lot of questions.
Yep.
But in terms of modeling, you had mentioned heuristic models, and I'm wondering if your colleague Paul Stanzel, has he published, or is he willing to share the actual model and the data directly?
Yeah, I can give you a link to his paper.
Okay, cool.
Yeah. It's based on Rob Wood's heuristic model, which is a paper that you can just find anywhere on Google.
Okay, well, any link here as a starting point would help.
Yeah, right. Okay.
Thank you.
Send Greg.
Or you can share it if you have time in the chat.
There's all kinds of things.
Okay. Well, any help would be appreciated, because I'd like to, as you say, the key is the model itself, and
Right.
Yeah.
How much of a mathematician are you, Greg?
Well, I mean, I'm trained, in physics, and so I think I could handle it. It's a question of how long. Plus, you use these days an AI to help you through the calculations.
Yeah.
So I'm quite happy to receive a technical paper.
Great.
All right. But it may take me a while to plow through, but that's what I'm after.
Yeah. Let's bring it up. Let's show you here. So very briefly, bring this up. It's called. So there's different papers actually. Let's go here very quickly. People. Where's my people? Paul. So it's called MCB using AS. So this is what his papers tend to look like. there it is there. And so yeah, it's pretty dense. We get in excuse me, pardon me. We get lots of stuff like this. Working out the temperature change, how to actually bring the temperature down again was, you see, we're only how many pages? 63 pages. It's pretty dense. There's a lot to get through here.
I guess the bottom line is, what are the equations? I see now we come to equations. Those are the ones that I'm actually want how he does the modeling itself. Yeah. So that's perfect.
He'll be delighted actually for you to look at that. He'll be very happy, and for you to feed back to him as well. Sure. Ron, please.
Yes, thank you, Clive. I'm still on my iPhone, so here I think I can open my. I put some stuff in the chat, and so it's great work. It seems like some really great ideas, and I hope this moves along and you get some acceptance. I just kind of raised the kind of obvious points that there's the unevenness. So I think it would be better when you're talking about MCB and tropospheric cooling in general to frame it as let's try and cool where we can, where it's most needed, extreme events over the reefs and things like that, because when you get into global cooling, the problem is it's very uneven. It can be very uneven. You do wherever the clouds are, wherever they're best, and you get these kind of very uneven effects that don't really work very well for global cooling. That's Walker Lee and all those people did those modeling studies of that. And so that's one thing, but I don't want to diminish what you're doing. I think it's great stuff, and we really do need to work on this. And the other point is, with regards to the IMO, I think the best framing is, look, we have an emergency. We have 10 or 15 years. We need to do something quick to get some cooling, and the quickest thing to do is just to relax the damn regulations, and more administrative burden. I mean, that's that word, as I put it in my note, to pose that against the huge devastating effects from more warming. So just do that, and these other methods need to be ramped up as soon as possible to replace so that we can actually put your regulations into effect and use benign forms of cooling, possibly, so that we had a discussion on this, I don't know, in some HVAC thing or whatever, but, that seems to me the best approach, because, it's not opposing the regulations. It's just saying we have an emergency. We need to do something quick. Let's just do that. And then we can go to your more, easier to enforce regulatory regime.
Yeah, great, Ron. My only comment is that they could relax the regulations and let ships, let's say they did in a hypothetical world, say, okay, you can go back to burning your high sulfur fuel again. It would have a slight cooling effect, but shipping lanes, they're not big enough to do enough cooling. So it'd help a bit, but it's like what I was saying, it's like putting your arm in the shade when the rest of you's in the sun. So that. It's better than nothing, but the best thing is to have these ships spread in the right areas where clouds brighten easier. These areas tend to be pretty empty, nothing much going through there, not enough clouds getting brightened.
No, I think I agree. That's high seas, right? We're saying relax on the high seas, and there was that early study saying you get actually most of the cooling by doing that, and you get most of the health effect by just enforcing them in the. I mean, that was that early study, and they should look at that some more. But just as an immediate thing, and then of course you're right. You want to. That's not necessarily optimal for but optimal depends, on what kind of harm you're trying to mitigate. So optimal would be to do this over, say, the Great Barrier Reef during marine heat wave events, stuff like that to prevent cyclones, tornadoes. So that's sort of, I mean, I think we agree on all this stuff. I'm just sort of raising the obvious.
Very good, Ron. Thank you for that. Yeah. Thanks for doing that. I do agree with your way of thinking. Thanks. Franz, please.
Clive, the IMO allows to dump the neutralized, if you use a scrubber devices on ships, they allow to dump the neutralized sulfate to the ocean. and you will not do anything other, because your sulfate is neutralized by ammonium. And so you showed one slide where you said you would acidify the ocean a little bit.
Yeah.
No, you don't acidify the ocean.
Yeah, because you send ammonia with it to make ammonium sulfate.
Yes.
And so it's not even a little bit.
Some, not a little bit.
Yeah.
Because ammonium sulfate in the ocean, the ammonium is transformed at once to nitrate. And this nitrate is taken up as a fertilizer by phytoplankton.
Yeah.
And is changed into organic nitrogen and ends later as N2 and goes up in the atmosphere.
Yeah.
So,
okay.
And also the SO4 is at last, because you fertilize a little bit the phytoplankton by your method. And so also you get no acidification, also not from the sulfate, because phytoplankton emits DMS, and the DMS, the natural emitted DMS, it reduces it increases the pH.
Yeah.
And also, if you fertilize phytoplankton, it produces it takes CO2, which is an acid, and changes it to organic carbon. So you will, at the end, I think, more alkalize the ocean, not acidify.
Right. Yeah. Okay.
That's it.
Thank you.
Another thing is, in one of the first slides, you mentioned the perm trias.
Yes,
the Permian trias.
The Permian extinction. Yeah. Yeah. That's just before the dinosaurs. That was. Yeah.
This is much more complicated. What you wrote, the 10,000 to 100,000 years.
Yeah.
Heating.
Yeah.
Because they make also stratospheric covering, so you get the temperature down. And then when it gets clear and the sun came again, and this happened surely often in this time, it goes up and down there, and you get sudden heatings and sudden coolings, and at the end you get the enormous heating. So it's much more complicated.
It's much more complicated than this.
Yeah.
This is a very big simplification.
Yeah. Yes.
Yeah. Thank you, Franz. I mean, just so everyone knows, Franz has been telling me these things since 2019. So what's that? 7 years, and I've learned so much chemistry from Franz, and also geology as well. So I'm not going to argue. I don't argue with that, Franz. This is only a simplification for everybody.
Yeah, I forgot one thing.
We've got to give time for other people, Franz.
Okay.
Yeah, no problem. Let's give some time for. Thank you, everyone. And let's move on here. So, yep. Where are we? So let's come back to our agenda. Thanks, everyone, for your comments. So we haven't got long. We've got 20 minutes. Yeah. Proposals to fund SRM, please, Glenn, please.
Okay. I'm going to be really brief here, and I'm not going to get into details, and I'll just take a couple of minutes. And let's see. So I'll turn on sharing. And
you should be able to do it. Yeah.
Yeah. Okay. So in theory, one could argue that the climate problem costs trillions of dollars. Therefore, we should be thinking about how to spend billions of dollars to save trillions. And that's billions of dollars for R&D, not for operations, but for R&D, because we have to do the R&D before the operations. And then the question is, where do you go to get information on spending billions of dollars on R&D. And one place is to go to this website, aplan2savetheplanet.org, and then in the menu bar, click on Documents, and then you get to this page here. And then you can scroll down, and there's the area here for stratospheric aerosol injection. And here's a $1 billion experimental research fund. So if $1 billion goes into SAI experiments over 5 years, what does that look like? This document describes that. And also, one could ask, what about equipment that does SAI, that's automated equipment where you have the monitoring is automated and the flying is automated, the refueling, the reloading is automated. All that equipment would have to be developed and prototyped and debugged. And this document here describes a $1 billion initiative to develop that equipment. And also there's a plan that describes how to go from where we are today to full-scale operations 15 years from now. That's a 7-page summary. So that's documents that describe SAI, but also you have the same thing with marine cloud brightening. You've got a plan, 7-page summary, along with $1 billion research proposals for MCB, experimental research and equipment development. But also the global climate models are not accurately predicting what we observe in terms of the average global temperature, the global warming rate, the albedo, the change in albedo over the last 25 years. All these things are not predicted by global climate models, which means they're incomplete. Then the question is, what experiments can we do to improve global climate models? And this document, it summarizes that. It's $1 billion worth of experimental research to improve global climate models. And they are needed to calculate how much sunlight needs to be reflected when and from where, if you are doing solar radiation management. But also, if you need green energy, let's say you're doing marine cloud brightening, and you look at the cost modeling and you need electricity, and the cost modeling is showing the cost of electrical power ranging from like 5 pennies a kilowatt hour to 20 pennies, and they're assuming you're burning fossil fuel. But another option is to have nuclear reactors where you automate the site construction of the nuclear power plants using custom machines that cost $1 billion to develop. And that's described in this proposal here. And then to make your liquid ammonia, you could have platforms of chemical processing equipment that connect directly to the nuclear reactors. That would cost maybe, I don't know how much money it costs, but anyway, this is a $1 billion proposal to work on that. This would drive down the costs of green liquid ammonia, which then could be fed into a high temperature fuel cell to generate electricity on a ship to do marine cloud brightening without emitting carbon dioxide from the fuel and at low cost. So these are examples of open source documents, which means anybody can copy, modify, use in any way for free.
Great.
So questions? And I'm going to be real brief here because there's other people who had some things to talk about.
Yep. Questions?
Thanks, Glenn. I'll try to take a look at some of your proposals.
Okay. Okay, next speaker.
All right, thanks, Glenn. Yeah, I think we said but last time, the problem is, there are people with money, but then they just say, who can we trust? Who do we trust to decide on, all these proposals? So they do have a bit of a problem. It's like, who are they going to trust?
What about you? You've got a trustworthy looking face. Would they trust you?
I'd love it if they would trust me. It takes several people. I work away on things closely with Paul, and then he just asks these awkward questions. He says these awkward things, and he says, where does it say that? Have you just taken that from the ChatGPT answer, or have you checked the answer? And often I'll say, oh no, I just took it from ChatGPT. He says, well, you've got to check the answer, haven't you? So you need a team of people. I think it has to be seen to be. This is how scientists work all the time. This is why scientists annoy each other so much all the time, because they're always asking awkward questions. And so these things, I think, don't happen overnight. That you get to know a group that's functional, that seems to be able to work in this way. They question each other. And science is a process that seems to produce. Jim Hansen describes this. Science the way it works is it produces in the end reliable results. It's not all reliable all the time, but in the end it comes out. Brew, please. Thanks, Glenn. Yeah. Brew, you need to unmute. Unmute.
Am I with you now?
Yep. Yes, you are.
Good. On the idea of switching back on the pollution from ships, I was looking at the GOES report, and that's 2023 when they did all of that sampling across the Atlantic. And they found an enormous amount of partially combusted carbon from shipping.
Mm-hmm.
And that is incredibly damaging because it collects forever chemicals and it damages the phytoplankton and the zooplankton because they found were absolutely really, really low. So we've made, I think, probably again, I'm looking for information to see if we have actually cleaned up the ocean surface a bit. Because the phytoplankton and zooplankton and the natural life in the ocean is the creator of natural cloud.
Mm-hmm.
And we may have just made a big gain back towards natural help. So I raise a massive question mark over the idea of taking a retrograde step, having fought like mad to reduce the amount of sulfur emissions, to suggest you go back to burning filthy bunker fuel in large quantities.
Well, it's still burning bunker fuel in large quantities. It has a lower sulfur content. So
it's what's emitting. Yes, it's what's being emitted, and but I don't know the answer to that.
Yeah,
but it would be interesting to discover.
Yeah, absolutely. Thank you, Brew. Okay, probably we should go around to the next. We've only got 12 minutes, so let's come back to the next one. Let's share and look at that. Yeah, I mean, we're all very much on the same page here, aren't we? So yeah, Greg, please, El-Nino or just underline.
Why don't you skip that? I don't think there's enough time for any reasonable discussion. Just
fair
go
enough.
on.
Sev, your invitation for people to identify countries to carry out cooling experiments.
Yeah, that's all I really need to say. It was really instructive having Singapore as an example, and it looks really good. I've sent a copy of it to Brian. But if other people are interested in seeing whether their country or some other country might be good, you can phrase it to an AI. In this case, just Google AI, and it'll give you an answer in a second or two. And it's quite easy to look at that to say, this looks good or maybe not so good. Okay, that's all.
Okay, thank you, Sev. Thank you. What else we got? We have, are you still with us, Brian? Brian, 2 o'clock in the morning with jet lag in India.
He's asleep in his chair.
All right, is he? Yeah. I'm actually quite glad to hear Brian's voice because he hasn't been well, has he? I think he works too hard. All right, so let's go to Ron. You've got 10 minutes, Ron, to talk about regeneration of ship tracks to avoid this Icelandic termination shock. I haven't heard anything about that. You with us, Ron? I think Ron is not with us anymore. Well, we've got open session then, haven't we? Or we could either, Franz?
I wanted to answer Propier's said ocean is full of waste from the ships, from the fuel burning of ships and so on. And this method you described for sulfur combustion, it can be used for ship scrubbing too. And you can make clean ammonium sulfate, which you can use as a fertilizer on the continents. And you can eliminate all other kinds of
pollutants.
pollution from the flue gas, like organics and hydrocarbons, and so which haven't burned and soot, and dust by simple using activated carbon aerosol cleaning before you neutralize. And this is a simple thing. And according to Seth's answer, he said, why don't you use iron 3-chloride for feeding the phytoplankton and making clouds? You can do it if you use iron 3-chloride as a catalyst for your SO2 oxidation, and it gives us ammonium sulfate dotation also into the cloud. It works very well also. And additional, white clouds have very small droplets, and very small droplets have positive surfaces, and they live longer than normal clouds, because these small droplets don't like to coagulate according to their surface loading. So, and this surface loading also induces to produce OH radicals and H2O2 within these droplets. And if you give a very slight amount of iron into these droplets, you will find a burst of OH radicals. And if you use iron 3-chloride, the chloride will transform by the OH radicals to chlorine, and these chlorine atoms produced, they leave the droplets because they like more the gaseous phase, where they meet methane, and you get a very good methane depletion within these white clouds. This you forgot to mention this, I think. And a little bit of iron is always good for the phytoplankton.
Absolutely.
Who's the gentleman that did that illegal ocean iron fertilization?
You're talking Russ George.
Russ George, yeah. I actually met him long ago, he told me that there was a time when they used to, because iron 3-chloride is used in wastewater treatment, and he said they used to put it out in great big ships and just dump it in the ocean.
Just dumping it. Whereas Seb's idea of buoyant flakes is far more elegant than what Russ George is proposing. Tip loads of stuff into the ocean and let it sink through the water column. Let's build little habitats for microorganisms.
Totally agree. Yes. All right, everybody. Well, I mean, we've run out of things to talk about. Should we just finish early today? Otherwise, we're kind of just all hanging around, wondering what to say. Unless someone's got another comment. Let's have an early night tonight. Thank you, everybody, for joining and giving me the opportunity to go through this, and for your feedback. As we'll keep going on emails, and I'll see you again in a couple of weeks.
Thank you.
Thanks, Clive.
Thank you. Bye.
Bye.
Thank you. Bye.
Bye.
Bye.